Given an integer array nums and a positive integer k, split nums into groups of size k where each group is k consecutive integers. Every value must be used exactly once. Return true if such a partition exists, otherwise false. Example 1, given this input with k equal to 4, we need two groups of 4 consecutive numbers. First group, 1 through 4. Second group, 3 through 6. Every entry is used once, so the answer is true. Example 2, given this input with k equal to 3, the array length is not divisible by k, so we cannot split evenly into groups of 3. The answer is false. Our mission is to split a pile of numbers into distinct teams of size k, where every single team must form a perfect, unbroken consecutive chain. A quick upfront check ensures our total card count divides cleanly by k. If it does not, we can shut down and return false immediately. When scrambled, it is hard to know where to start. But if we sort the numbers, the absolute smallest element on the board is forced to reveal itself. Because it is the smallest, it cannot live in the middle or end of a chain. It must be the anchor that starts our very first team. To process these chains efficiently without getting tripped up by duplicate copies of the same numbers, we convert our array into a stockroom inventory. This lets us see exactly how many copies of each card we have available at any moment. We pull our smallest available card, 1. Starting a chain at 1 completely locks in our next requirements. We are absolutely forced to find a 2 and a 3 to complete the team. We check our inventory, decrement their counts, and ship our first valid group. We advance our scanner to the next smallest available card, which is now 2. 2 demands a 3 and a 4. If a mandatory partner is ever missing or out of stock, the puzzle breaks instantly, and we return false. But since our parts are available, we clear out the stockroom cleanly and return true. We kick off our code with a quick optimization guard. We verify if our total number of cards can be divided evenly into teams of size k. If the modulo check fails, it is mathematically impossible to form the required groups, so we can immediately return false and save execution cycles. Now we build our frequency inventory. If you are using a language like Java or C++, you can load your cards directly into a self-sorting structure like a tree map. It automatically keeps your keys in ascending order under the hood. If your language doesn't have a built-in sorted map, like Python or JavaScript, don't worry. You can achieve the exact same result by using a standard hash map to count the frequencies, and then extracting and sorting a separate list of just the unique keys to serve as your roadmap. Now we enter our master loop, which runs until our stockroom is completely empty. In each iteration, we grab our starting point. Because our map is self-sorting, we can instantly query the very first key. This guarantees we are always anchored at the absolute smallest available card remaining on the board. With our anchor established, we must immediately validate a consecutive chain of size k. We run a nested loop from 0 up to k-1, checking for the existence of each successive number. If our map is missing any consecutive partner along this sequence, the chain is fundamentally broken, and our code instantly returns false. As each required number passes the check, we decrement its frequency in our stockroom. If a card's count drops to 0, we completely purge that key from the map. This keeps our inventory clean so that the next iteration of our master loop can correctly identify the next smallest anchor. The master loop circles back around. With 1 completely gone, our map instantly hands us 2 as the new lowest anchor. The code demands 2, 3, and 4, clearing out the remaining stock perfectly. The map goes completely empty, the loops terminate cleanly, and we return true. We've successfully validated our sets. Let n be the length of nums and k be the group size. With a sorted map, time is O of n log n, we insert n keys in logarithmic time, then each value is removed once through logarithmic map updates along consecutive chains. Space is O of U for the frequency map, where U is the number of distinct keys. Pseudocode for divide array in sets of k consecutive numbers, using a sorted map. If the array length is not divisible by k, return false immediately. Return false. Create an empty sorted map named counts. For each number in nums, increment its frequency in counts. While the map is not empty, read the smallest key as first. For I from 0 to k minus 1. Set current to first plus I. If counts does not contain current, return false. If the count for current is exactly 1, remove current from the map. Otherwise, decrement counts at current by 1. When the map is empty, return true.